Hello and welcome to another one of our online lecture videos for differential equations. And today we're going to be talking about stability in the phase plane. So first we're going to talk about some key terms, and we're going to talk about what type of situations we can encounter and what the main contenders are for the section. So key terms for critical points and equilibrium solutions. First we talk about stability, stable versus unstable. We say a critical point is stable if as t increases, our trajectories, which are the particular solution curves, approach the critical point. And t doesn't always have to denote a measurement of time, but typically it does, depending on context. We'd say, well, as t increases, where do our trajectories go? Do they approach the critical point, or do they move away from the critical point? So stable means that as t increases, those trajectories approach the critical point. Unstable, we say a critical point is unstable if as t increases, our trajectories, or particular solution curves, move away from the critical point. And if a critical point is not stable, it is unstable. So it has to be one or the other. And here's a little note about eigenvalues. We're going to talk about eigenvalues and how they come into play more so in the next section. For this first section, we should be able to introduce the material in a bit of a different way with some different intuition. I have some pictures here to accompany. We have an unstable node, and here we're sort of looking at the center here at 0, 0 as perhaps being where the equilibrium solution would be. And notice the trajectories are moving away from it, so sort of pointing outward, so moving away. So there's an unstable node for you if you want to check it out. Proper node, we say a proper node occurs when we have two eigenvalues of the same sign. In this case, we either have a proper stable node or a proper unstable node, depending on whether the trajectories approach or move away from the critical point. An improper node, so improper node will occur when we have repeated eigenvalue. In this case, our trajectories or particular solution curves will travel past the critical point slightly and then curve back towards the critical point. An improper node may be stable or unstable. And when I think about the terms proper and improper node, I think about what the eigenvectors are doing as well. So if you want to sort of talk a little bit more about this, I would say, well, wait until maybe we see some more material, but then also feel free to ask me. I'm happy to sort of talk about this. So here we have an example of an improper node that is unstable. So here we see our trajectories are moving away from the critical point. And then here we have an asymptotically stable improper node, where here we have our trajectories are moving towards the critical point, so showing that stability there. Asymptotically stable. We say an asymptotically stable node or spiral occurs when all of the trajectories, or the particular solution curves, move towards the equilibrium point when t increases. And this is characterized by having two negative eigenvalues. And again, don't really worry about the eigenvalue information. We'll talk about that in the next section, and it's really going to bring everything full circle, so to speak. But here we have asymptotically stable. We see our trajectories are moving towards the critical point there in the center. So the arrow is pointing inward then. Center. So a center is a great example of something that is stable, but not asymptotically stable. So we say a center is always stable, and this is characterized by having a complex conjugate pair of eigenvalues with no real part, meaning the real part is 0. In this case, we have a sinusoidal solution, remember, built up of cosines and sines only, that will circle around the equilibrium point without moving towards the equilibrium point. So in this case, we say a center is always stable, and it just sort of looks like we have these rings traveling around the equilibrium point. So we say center is always stable, but not asymptotically stable. Spiral point. We have a spiral point is characterized by a complex conjugate pair of eigenvalues with a non-zero real part. So here the real part is there. We think about how this would look with our characteristic equation, how the solutions would look. This is going to build not only cosines and sines, but those are going to be multiplied by an exponential function as a factor. So we say in this case we have a sinusoidal solution multiplied by an exponential function that will circle around the equilibrium point and gradually move towards it like a spiral. Now a spiral point may be stable or unstable, and it depends on the sign of the real part how the trajectories are going to be behaving. So here I have an example of a spiral that's unstable. So notice the trajectories are moving us outward away from that equilibrium point in the center there. And here I just have an example of a visualization of an asymptotically stable spiral. Here our trajectories move in towards the equilibrium point. Saddle points, very fun to talk about. In a saddle point, we get some disagreement in behavior, and some of the solutions will begin away from the critical point, and as t increases, they start to move or sort of creep towards the critical point, only to eventually diverge away from the critical point. So a very interesting behavior. At first, it sort of looks like it's moving towards the critical point, and then it sort of darts away almost at the last second. And we may have that some solutions move towards the critical point, while some solutions move away from the critical point, and this would be characterized by real eigenvalues of different signs. We say then that a saddle point is unstable. So this sort of interesting behavior sort of fakes us out a little bit. But saddle point, there's a picture of how a saddle point would look. And then just a couple of other key terms before we start looking at some examples. We have a source. A source is unstable. So the idea of a source, we could think about sort of having a node or our equilibrium point, and then we have trajectories moving away from it. We do a cool little dance move like this. And then we have a source. A source is unstable. We have a source if we move away from a critical point, whereas a sink means that we're moving towards, so that would be stable. So a sink is stable. We have a sink if we move towards a critical point. So source and sink are the two other key terms that we may end up using. Source is unstable, moving away from the critical point. Sink is stable, where we're moving towards the critical point. Now let's see some examples, and I think this is going to be a nice lecture. I think you're really going to actually enjoy this one. We'd like to find the equilibrium solution, here for x sub 0, of the given second order differential equation. Here we have x double prime plus a function f of x and x prime equals 0. We'd like to use computer systems to help us construct phase portraits and direction fields for the equivalent first order system, where x prime is equal to y and y prime is equal to negative f a function of x and y. So sort of like this up here, where we're saying if y is equal to x prime, we can substitute a y in there, and then we solve for x double prime, and from that we build a system of first order equations. Thereby, we'd like to ascertain whether the critical point at whatever the x value is, comma 0, so we're being told the y value is 0, whether or not that looks like a center, a saddle point, or a spiral point of the system, and that would be after we look at a visualization. And let's go ahead and take a look at this first example. So here we have x double prime plus 4x minus x cubed equals 0. First thing I want to do is I want to solve for x double prime. So that means x double prime is equal to, I can add x cubed over, and then subtract 4x. And now what I want to do from here is I'd like to build this into a system of first order differential equations. So I'm going to start with this sort of substitution here, where we're going to let x prime be equal to y. And if I differentiate both sides, this means that x double prime is equal to y prime. So if I take a look at what I have here, I can replace x double prime with y prime. So here we get y prime equals, and there's no mention of x prime here, so we would just get x cubed minus 4x. And then the substitution as well right here, x prime equals y. And this is going to be our system of first order differential equations. So we have x prime equals y, and then y prime equals x cubed minus 4x. So there's our system of first order differential equations. Now, if I'm looking to find the critical points to the system, I would like to set the derivatives equal to 0. So I want to set x prime equal to 0, and I want to set y prime equal to 0. Now, if x prime is equal to 0, since x prime is equal to y, this means y is equal to 0. It solves right away, immediately. However, if y prime is equal to 0, well, that means that x cubed minus 4x is equal to 0. And we can go ahead and factor here, so I can bring out a greatest common factor of x. That's going to leave me with x squared minus 4, and then equals 0. And so then here this means, well, I could factor this further, right? So we'll do x, difference of perfect squares factoring. So we'd say x minus 2, x plus 2. So here we get either x equals 0, x equals 2, or x equals negative 2. So 3 different x values. But keep in mind that we just got the one y value. So that means that this is going to build 3 different critical points, and that the y value is the same throughout. So we have our critical points. And all of them with y is 0. But then the x values are going to change, right? So x could be 0 and y is 0, or x could be negative 2 and y is 0, or x could be positive 2 and y is 0. So we get these 3 critical points to consider. Now we are going to talk about how we can determine the behavior without necessarily having a visualization first. But for this first example, so we went through, we found the critical points. Now we'd like to take a look at a phase portrait, and from that phase portrait, looking at it visually, try to figure out what the behavior is at these 3 critical points. Now, so let's go ahead and start with 0, 0. So right in the center, x is 0, y is 0, and here I have an example, well, 2 sort of pictures for us to look at. So 0, 0 right here in the center, and if I notice the behavior around it, so you have sort of 2 solutions, 2 particular solutions around it. We're here looking at a stream plot diagram, thinking about 0, 0 right in the center. What does the behavior sort of remind us of? If I had to pick from the original list, this one I think is kind of a dead giveaway. That looks like a center. So I would say at 0, 0, we have a center, which we can mention then a center is stable. If I want to sort of flip back, where do we get the picture? Right here, center is stable. So here we're just sort of circling around the critical point, but not moving towards it or away from it. And that's what it looks like we have at 0, 0, is that stable center. Okay, well, what about at negative 2, 0 and positive 2, 0? We would look at these one at a time, but when looking at them, it sort of looks like the behavior at negative 2, 0 and positive 2, 0 is kind of similar. It sort of builds this interesting symmetry here to our picture. So sort of looking at it and trying to figure out where it is and what that behavior is, I think this one is a bit tricky from the phase portrait. And certainly we get better with practice the more of these examples we see. But if you had to, say, pause the video and take a guess, what do you think that behavior is at negative 2, 0 and positive 2, 0? If you said saddle point, I would agree with you. So I will admit, I think it's a little bit tricky to see from the picture. So we are going to talk about how we can determine this without sort of, looking at it and trying to sort of guess more or less. But these look like, to me, to both be saddle points. And saddle points are unstable. Sort of this interesting behavior where kind of looks like, depending on where we're looking, that it might be headed towards the critical point, but then only to move away from it, sort of at the very end. So very strange and curious behavior with the saddle points. That looks like what's going on at negative 2, 0 and positive 2, 0. And then, so these are some nice phase portraits. In particular, the stream plot is something very quick that you can do online. But I think it would be great to use this as an opportunity to go through these examples that we see today and actually build a phase portrait through Python. So that would be something to keep in mind for the lecture as well. Well, let's take a look at some other examples, and let's move away from what we've been doing and see if we can determine the behavior before looking at a phase portrait, and then use the phase portrait to verify what it is we're thinking. So here we want to solve each of the linear systems to determine whether the critical point at 0, 0 is stable, asymptotically stable, or unstable. Then we're going to use the computer system, construct the phase portrait and direction field, and then we're going to try to confirm what we've seen. We're going to try to determine whether or not what we have is stable or unstable, try to identify it as either a node, a saddle point, a center, or a spiral point. And we'll see lots of examples today. Now, first of all, I have dx dt equals negative 2x and dy dt equals negative 2y. If you'd like, you could rewrite this with the prime notation. X prime equals negative 2x, y prime equals negative 2y. And you could show that this means that 0, 0 is a critical point. Certainly, if x prime is equal to 0, it follows that x would have to be 0. And if y prime is 0, well, then y would have to be 0. So 0, 0 is what we're talking about here for the critical point. But now I'd like to get an idea as to how our solutions look. In doing this, we could actually solve this by inspection. But I think one of the fastest ways to solve it using some method would be with the characteristic equation. So turning these into homogeneous differential equations, we would say x prime plus 2x equals 0. And similarly here, y prime plus 2y equals 0. Getting that very small characteristic equation, r plus 2 equals 0, means r equals negative 2. And same for this one. So here on y, we get also r plus 2 equals 0, r equals negative 2. Now this isn't even something we would have to do. Like I said, I think you could solve these by inspection even. But building our solutions, we would see that our solution on x gives us that x, a function of t, is equal to some constant c sub 1 times e to the power of negative 2t. And y should look the same, right? So we'd say y at t. I don't know that its coefficient is necessarily the same, so we'll say c sub 2. But it is that exponential function e to the negative 2t. So here we build our solutions for x and y. And they're both really of the same general form. Now, something that I think is worth pointing out here is what happens as t increases. So that would be next for us to sort of talk about what happens as t goes to infinity. Well, keep in mind, we could rewrite these. We could say x is equal to c sub 1 divided by e to the 2t, and y is equal to some constant c sub 2 also divided by e to the 2t. And as t gets very large, as t heads to infinity, this exponential function is unbounded, so it also heads to infinity, but it's in the denominator. So where is that going to go? Well, that's going to 0 for both x and y. If we say for very large t, this gets smaller and smaller, smaller meaning headed to 0. But remember that x is 0, y is 0 is our critical point. So this means as t goes to infinity, x and y have trajectories that approach the critical point. So we can sort of mention here, as t goes to infinity, we approach 0, 0. We approach the critical point. Which means that we have something that's going to be stable here. So here we have a stable node in this case. Something else that I think is interesting about these examples is that we can get an idea as to how our trajectories are going to look. So how our trajectories are going to look, and this would involve just a little bit of extra work, but I think it's worth it to sort of do. If I go here to y, since x and y are practically the same, I can develop a relationship between these two. So here we'd say y is equal to, and what I can do is I can multiply this by c sub 1 over c sub 1. So for example, I would take c sub 2 multiply by c sub 1 divide by c sub 1 times e to the negative 2t. And you'll notice here that I wrote this in sort of a very telling way. C sub 1 divided by c sub 1 would just cancel, But here, notice I put c sub 1 next to the exponential function, and then I put the divided by c sub 1 right under c sub 2, so that we can really notice that in all of this, we have some mention of x. Right? X is c sub 1 times e to the minus 2t. So what we could say in general, we could say y equals c sub 2 divided by c sub 1. That's just some constant, so let's call it k. And c sub 1 times e to the negative 2t, well, that's x. So y is really some constant times x for some constant k, right? Y is equal to k times x. Which means that although we have this stable node here, we can actually get an idea as to how our trajectories will likely look. So from this information, I would start to wonder, well, okay, so this means that perhaps the trajectories are going to look sort of linear. Let's go ahead and take a look at what we've determined here. So we've already said a lot of stuff here. We said 0, 0 is our critical point. We said that we have stable critical point. And then we even found a relationship between the expressions for y and x, leading us to think, well, there's some kind of linear behavior happening here. Now for the best part, we look at the phase portrait to try to determine if what we said is all nonsense and garbage or if we were onto something here. So here we got a couple of examples of how this would look. 0, 0 being right in the center, and all the trajectories are pointing in towards it, which means we are stable. I like this stream plot here with all the arrows pointing in. And then we notice too that it does appear to have sort of this linear type of behavior in the trajectories. So I think that was worth sort of mentioning, although maybe extra, maybe unnecessary to do that. I think it helps us just get a little bit more insight into what's actually happening here into our system of first order differential equations. Pretty cool. Let's take a look at another example. So again, here we could start by rewriting into our favorite notation. We have x prime equals negative 2x. We have y prime equals negative y. And then here we could work with a homogeneous equation, say x prime plus 2x equals 0. Y prime plus y equals 0. And I've seen this before, but I'll still go through the characteristic equation. This is r plus 2 equals 0, or r equals negative 2, meaning my solution for x is some constant c sub 1 e to the minus 2t. But y prime plus y equals 0 is new, so I can get my characteristic equation for that. So r plus 1 equals 0, or r equals negative 1. So we get y a function of t is some constant c sub 2 times e to the negative, whoops, no, yes, e to the negative 1t or e to the minus t. And talking about the critical point that we have here, we didn't go through and verify, but if you set x prime equal to 0 and y prime equal to 0, it certainly follows from there that x would have to be 0 and y would have to be 0. So we have the critical point 0, 0 that we're talking about. Now with each of these, we want to think about the behavior, right? Is this going to be stable? Is it going to be unstable? Well, think about rewriting this. So we would say as t heads to infinity, we have x is c sub 1 divided by e to the 2t, and that's going to head to 0. And y, which is just c sub 2 divided by e to the t, would also head to 0 as t increases. And, similar argument to the last example, we would say the exponential function is unbounded as t goes to infinity, and dividing by it gives us these smaller and smaller values. So we would say as t increases, our trajectories move towards the critical point. Zero, zero, which means that we are stable. So here we have an asymptotically stable node. Now, like in the last example, if I want to try to find some relationship between these two, I could. And this one's a little bit trickier, but for example, if we took a look at y squared, if I square what I got for y, well, that would be c sub 2 e to the minus t times c sub 2 e to the minus t. And if I were to multiply this together, whatever c sub 2 is, well, now I'm squaring it, so that's c sub 2 squared. And then e to the minus t times e to the minus t, well, we would keep the base and add the exponents. That gives me e to the minus 2t. So here we get y squared equals c sub 2 squared times e to the minus 2t. But I can do a similar trick to what I did before, where here I can just multiply by the expression 1, c sub 1 divided by c sub 1. And notice that now I'm talking about x, right? X was c sub 1 e to the negative 2t. So what can we say from all of this? Well, we can say here that y squared is equal to, now c sub 2 squared is just a number, divided by c sub 1 is just a number, so all of this is some constant, let me call it k, times, here c sub 1 e to the negative 2t is x. So we get y squared equals k times x. Or if we want to try to solve for y, we would say y is equal to plus or minus the square root of kx. But so either way here, we're looking at this, we should see something, perhaps a bit parabolic in nature. Definitely not linear, right? So here, when we're approaching that critical point, we said we're stable. When we're approaching it, we expect something that's not linear in our trajectories. And just some interesting way to compare what we get for, y and x, so that we can try to see some relationship between them, I think is always good to do. All right, let's take a look at it. So here we have 0, 0 is our critical point, and the stream plot as well. Everything is headed towards the critical point, so we are in fact stable. And then here we notice that our trajectories, unlike that previous example, are not moving in a linear fashion. There's definitely a nice sort of curve to them. So we have that asymptotically stable node at 0, 0, and we can verify that visually with our phase portrait. Let's take a look at a next example. So now we have, if I want to rewrite it with that shorthand notation, we have x prime equals y, and y prime equals negative x. And still, if I were to set x prime equal to 0, that means y would have to be 0. If I were to set y prime equal to 0, well, 0 equals negative x means x would be 0. So the critical point is still 0, 0, just like we've been doing for all of these. But now when I go to solve, it looks like this is a little bit more complicated. And since I have x prime equals y and y prime equals negative x, I wouldn't really be able to work with the characteristic equation right away. However, what I could do, for example, is I could go ahead and use something like the elimination method. So here, if I differentiate both sides of this x prime statement, I get x double prime equals y prime. And then I can substitute into the other equation. Say y prime is equal to x double prime. So then x double prime equals negative x. And now I can set this equal to 0. So x double prime plus x equals 0. So I have my homogeneous differential equation, second order. And I can go ahead and work with the characteristic equation now. So here x double prime gets replaced with r squared. And then plus 1 equals 0. If I try to solve this for r, well, that means r squared is equal to negative 1. So r is plus or minus the square root of negative 1. or that means r is plus or minus I. But notice that the real part is missing, meaning the real part is 0. So when I go to build the solution on x, we would say, I'll leave some space here, but we would say x at t is e to the 0 t times some constant c sub 1 cosine at t plus some constant c sub 2 sine at t. And that e to the 0 t is just 1. So here we're just left with x, a function of t, is c sub 1 cosine t plus c sub 2 sine at t. Well, okay, what about y? Well, remember from that first differential equation that we wrote down, y is equal to x prime. So meaning if I differentiate x, that's going to give me y. So here we'll say x prime at t, but that's really equal to y at t, is just the derivative here. And if I differentiate, derivative cosine gives me negative sine. So negative c sub 1 sine at t plus derivative of sine is cosine, so c sub 2 cosine at t. And so they were able to, using that elimination method, solve for x at t and y at t. Now, if I think about the behavior as t increases, so that's what we would want to maybe talk about next. We'd say as t goes to infinity, let's look at x first. As t goes to infinity, well, this doesn't really necessarily head off to infinity or head to the critical point at 0, 0. This just sort of oscillates, right? Here, cosine, depending on what I plug into it, is somewhere between negative 1 and 1. And sine, depending on what I plug into it, is somewhere between negative 1 and 1. And it just sort of keeps going on and on and on. So the fact that t keeps increasing doesn't really change the behavior here of cosine and sine. So as t goes to infinity, we would say x and y oscillate, and they don't necessarily really move towards or away from anything. And maybe that's sort of a bit of a hint as to what the behavior is here. But I think that we can also see what the situation is going to be like if we try to maybe eliminate some parameters or work with building a relationship between x and y. And I think doing this is a little bit tricky to maybe see at first if you haven't done something like this before, but a great trick in case of dealing with these cosines and sines would be to actually square x and square y and add those two together. Now, if I were to square x, that would be c sub 1 cosine t plus c sub 2 sine t, and I'm going to square it, plus y was negative c sub 1 sine t plus c sub 2 cosine t, and we're going to square that. So what does this give us? Well, here, think about foiling. C sub 1 cosine t times c sub 1 cosine t gives me c sub 1 squared cosine squared t. C sub 2 sine t times c sub 2 sine t gives me c sub 2 squared times sine squared t. And for the outer and inner term, those are going to be the same, so I'm going to be doubling it, and it's going to be the product of the two terms in the binomial. So that's a plus 2 times c sub 1 times c sub 2 times cosine t times sine t, and then I'll keep adding to this because now I want to square the next. So plus negative c sub 1 sine t times itself gives me a positive c sub 1 squared sine squared t. C sub 2 cosine t times itself gives me c sub 2 squared cosine squared t. And then same idea here for the outer and inner terms, and combining them, it's going to be the product of the two terms twice over. So here it's going to be a negative times a positive, so that's negative 2 times c sub 1 times c sub 2 times cosine t times sine t. And so this is what we get for all of those terms from foiling, multiplying this out. I want you to notice that the outer and inner terms between the two squares that we've done actually cancel. We have positive 2 c sub 1 c sub 2 cosine t sine 2t, and we have a negative 2 c sub 1 c sub 2 cosine t sine t. So those are going to cancel, and we're left with, so I'll write it underneath, that x squared plus y squared is equal to, now let me write it so that the like coefficients are next to each other. We have c sub 1 squared cosine squared t plus c sub 1 squared sine squared t plus c sub 2 squared sine squared t plus c sub 2 squared cosine squared t. And if I factor those like coefficients out, I'd say, well, here I have c sub 1 squared times in parentheses cosine squared t plus sine squared t. And then plus here, if I factor c sub 2 squared out, this would be sine squared t plus cosine squared t. We see inside the parentheses, that's just our favorite identity, right? That gives us 1, sine squared plus cosine squared of the same argument. So c sub 1 squared times 1 plus c sub 2 squared times 1. And so here we get x squared plus y squared equals c sub 1 squared plus c sub 2 squared. Now that's not even where we're going to stop with this necessarily, because I want you to think of it this way. C sub 1 is just a number, so c sub 1 squared is just a number. C sub 2 is just a constant, so c sub 2 squared is just a number. And a number plus a number is just a number. So in a very general sense, we have x squared plus y squared equals k. And if we've seen this before, we probably remember, hey, this is the equation of a circle. And we have a lot of hints now that are sort of all pointing to the same result. And we even talked about this back when we went through the list that we had. So let's go back to the list. I think we're probably all thinking the same thing. You're probably yelling it at the computer screen right now. And I can't hear you because I'm too old. But let's go back here. I think we're all thinking, hopefully, here. So a center, a stable center, characterized by a complex conjugate pair of eigenvalues where the real part is equal to 0. With a sinusoidal solution that was circling around the equilibrium point without moving towards it. We say a center is always stable. And that's really what we have here in this case. Hopefully we've done enough to sort of justify it or to hint at it through our work. Yeah, that equation of a circle really sort of pushes that idea home. So I would say here we have a stable center at 0, 0 is what we're noticing. Let's see the face portrait. Yeah, right? Bullseye. Get it? Kind of looks like a dartboard. So that's what we have. So stable center. Center is always stable. Just sort of circling around the equilibrium point, never really moving towards it nor away from it. Let's take a look at one more example, and then we'll talk more about this and be able to generalize even further. We're going to bring eigenvalues into play in the next lecture. And here we have x prime equals 2x, y prime equals 3y. And you can see if x prime is equal to 0, then x would be 0. If y prime is 0, then y would be 0. So we have a critical point at 0, 0. These ones aren't so bad. If I want to solve them, I can just use the characteristic equation. So x prime minus 2x equals 0. And then here, if I want to set this equal to 0, y prime minus 3y equals 0. The characteristic equation here on this x prime equals 2x gives me r minus 2 equals 0, or r equals 2, meaning that x at t is some constant c sub 1 times e to the 2t. And solving for y, with y prime minus 3y equals 0, we get characteristic equation r minus 3 equals 0. So then r equals 3. So that y at t is some constant c sub 2 times e to the power of 3t. Now, once we build these sort of general solutions, this is where we really like to look at what happens as t goes to infinity. So as t goes to infinity, x, which is equal to c sub 1 times e to the 2t, well, now we have a problem, because notice that the exponent doesn't have a negative coefficient. It's an e to the 2t. So as t gets very large, the exponent gets very large, and the exponential function gets very large as well, and grows so that it's unbounded. So then this is going to head to either infinity or negative infinity, depending on what the sign of c sub 1 is. So say this heads to plus or minus infinity. And same with y, right? Y is also an exponential function. And the exponent here is 3t. So as t goes to infinity, well here, in this case, we're going to become unbounded. And then c sub 2 is the coefficient that determines the sign, but this is going to head to either plus or minus infinity. And this certainly does not head towards the critical point. So we would say as t goes to infinity, we move away from the critical point 0, 0, which means that we are unstable. So here we have an unstable node. Since it's unstable, that means our trajectories are going to be moving away from the critical point. If you'd like, you could try to still build a relationship between x and y from their solutions. Though for something like this, I don't really know if it's, I guess I would say, as important. But we can still do that with algebra. So for example, if I take x and take a look at x to the power of 3/2, that would be equal to c sub 1 e to the 2t to the power of 3/2. So my coefficient c sub 1 gets affected by this new exponentiation. So we have c sub 1 to the power of 3/2. And then we have e to the power of 2t to the power of 3/2 as well. And here where we're re-raising, that means we multiply the exponents. So we get x to the power of 3/2 equals c sub 1 to the 3/2 times e to the power of, here the 2's cancel, we're left with t times 3, or that's 3t. And then from here we can try to introduce some mention of y. So we could say x to the power of 3/2 is equal to c sub 1 to the 3/2 times e to the 3t. But then I can go in here and multiply by sort of a clever form of the number 1. I could multiply by c sub 2 divided by c sub 2. And there I see my expression for y, c sub 2 e to the 3t was y. So we get this kind of interesting relationship where we could say x to the power of 3/2 is equal to, now c sub 1 to the 3/2 divided by c sub 2 is just some constant, provided there's no sort of issues with what the numerical values are. So we just call that some constant k, times, but here c sub 2 e to the 3t is y. So we get some interesting relationship between x and y. And here, since k is just some constant, some coefficient, we could divide k over and say, well, then y is equal to some 1 over k times x to the 3/2. And 1 over k is just some coefficient, so we could perhaps call that something else, call it c, for example. Just some constant c times x to the 3/2. So some relationship there between x and y if we're interested in it. We already said that this is going to be unstable, that our trajectories are moving away from critical point 0, 0 as t increases. Let's see. Let's take a look. Yeah, so here if we take a look at what's going on, we notice that now the arrows, it's like you can't get away from the critical point any faster. What's the rush, right? Here we notice that the trajectories move away from 0, 0. So moving away from the critical point. All right, that's it for the section. Next time we're going to talk about how we can start bringing eigenvalues into play, and we're going to see that we can actually determine a lot of this useful information very quickly for a system. So using the eigenvalues. But that's it for this section. Let me put the homework in the homework jar. Please take a look at the homework on our online homework platform. Let me know if you have any questions, if you want to talk about this further. I hope you found this information interesting. I think it's really nice to go through these problems and see the visualizations. Try going through and putting some of these through Python so you can get comfortable with doing that on your own. And I will see you for the next one. But until then, remember to always keep learning, keep dreaming, and follow your heart. I'll see you.